All right, guys, welcome to Lab 7 on igneous rocks and volcanoes. I'm not going to go over every slide in the PowerPoint since you will only be using a few slides in this PowerPoint. So let's get started. So the first part of the lab is going to deal with this term called viscosity. And you're going to be looking at three different viscosities and how they pretty much how viscosity affects those liquids and then eventually affecting igneous rocks. And what viscosity is, it's defined out in the first question. It's pretty much a liquid's resistance to flow, to water. And the reason viscosity is important is because of magma, or pretty much lava, essentially. Lava underneath the Earth's crust. And the reason this is important is it affects how igneous rocks are formed. It affects cooling. And the biggest thing that affects viscosity itself is essentially temperature and the composition of the magma. So to kind of back up a little bit, the way magma moves is based off its viscosity, and viscosity is based off of composition mainly, and temperature. So how the magma moves is viscosity. How pretty much any liquid moves is viscosity. And this is discussed a little more in the description for part 1. So this slide, again, this is just for your reference. You don't have any questions really dealing with this, but viscosity of the magma does also kind of affect the type of eruption that volcanoes have, and these are the 3 different types. All right, so now the next part is going to be igneous rocks, and in particular, how to identify them. So just some background on igneous rocks. It's pretty much igneous rocks pretty much form from 2 main components, which is essentially heat and pressure. So when you have magma, either near the Earth's surface or pretty much above the Earth's surface, which is pretty much lava at that point, when it cools and hardens, that's when you get the formation of igneous rock. That's where the term igneous comes from heat. So the solidification of the magma is how you get igneous rocks. And again, composition is pretty much almost everything. Pretty much how fast the magma cools and what is within that magma is pretty much what affects the type of igneous rock you have, or the exact igneous rock you have. And the reason this affects the igneous rock is because different minerals have different melting points and they have different solidifying points. So kind of think of ice cream compared to an ice cube. That's different viscosity, different solidifying points, different melting points. It's kind of the same with different types of magma, with different compositions of magma and different minerals within the magma. And so now the next part, when you're identifying these igneous rocks, the main thing, I'll get into it a little bit more, you're going to be looking at crystal size or grain size within the rocks. So these are just examples. So slower cooling magma with large minerals, an example of that with large crystals is granite. That's just an example. So when you have slower cooling slower cooling rock with large crystals, you'll have more examples as well. But you'll have granite. And then just the reverse of that, something that cools very fast and has small minerals is going to be basalt. These are just examples. And now the quickest cooling, the rock that forms from the quickest cooling, if you will, is going to be called obsidian. Obsidian will be pretty unique. It pretty much looks like black glass, if you will. You won't be able to really see any minerals in it. You'll be able to identify that pretty quickly. So obsidian, black glass, pretty much the easiest way to memorize that. You guys aren't this. There are no questions really pertaining to this in the lab. This is just pretty much for your own use. These are just the types of igneous rocks: intrusive, and then you have extrusive, and they're pretty much straightforward. Intrusive within the Earth, extrusive near or outside of the Earth's surface. Okay, so the three main things you're going to be looking for when you're identifying these igneous rocks, there's a flow chart, anyways, that you'll see when you get to it. You're going to be looking at first. It's crystal size and coarse versus fine grained. Then it's color. And then from there on, pretty much its composition. And just a few notes about igneous rocks. Obviously, so they don't contain layers. That's a different type of rock we'll go over later in the semester. But igneous rocks, they're not going to contain visual layers per se. Like it won't look like a tricolor cake, if you will. It won't look, igneous rocks usually won't look like that. They are varied in color, and color will actually help you diagnose these igneous rocks more so than it did with the minerals. And crystal size, again, is going to be, color and crystal size are going to be your two main things. So here's a good example. Here's a good visual of kind of grain size. And this is good for a reason, because you have a penny to reference. So if we look on the left here where it says coarse grained, you can see this igneous rock. You can see multiple colors, and you can see these crystal grains, if you will. You can see multiple colors. You can see gray, you can see black, you can kind of see white. And at least compared to the penny, they're relatively bigger. They're not the biggest you'll see, but they're bigger compared to the right image here. But let's stick on the left. So this would be considered coarse grained. Just to give you an example. And now the opposite of this would be over here to the right. Fine grained is, again, now you can see the crystals. That's just because it's got a different color than the rest of the crystals in here, but they're much smaller, especially if you compare it to this penny. So if you look at the penny and then you look at the dark spots on this igneous rock to the right, you can see they're much smaller. As opposed to the left, they're relatively bigger. So this is a good visual. Again, because the first thing you're going to have to identify is it mostly a coarse-grained igneous rock? Is it a fine-grained igneous rock? Or there's a few other options. We'll get to those. But just being able to identify coarse versus fine-grained with amongst crystals within the rock, that's going to be very helpful. And then, so the next part's going to be color. Let's stay here for a second. So another aspect of these rocks is going to be something pertaining to not just its grain size, but what type of grains are within the rock. So these rocks are pretty good because they're all relatively one grain size. So this rock to the left here, it's all relatively coarse grains, and they're all relatively the same size. And then this rock to the right here, the fine grain, they're all relatively fine grain crystals. One other thing you guys will deal with is something, another section you'll look for is coarse grain coarse grain fragments or fine grain fragments. Those are the next two sections on that mineral identification, or it's the rock identification chart that's in part 2. So, or part 3, I believe. So like this is a good example of on this top picture here. This is a good example of large crystals, large grains within small grains, if that makes sense. I don't want to confuse you guys, but if we take, so this is pretty much taking, so this image here to the right, this fine grain image here, it's pretty much like taking that image and placing larger crystals within it. That's what this would be. So this top picture right here, this top picture right here would be coarse grain fragments. It'd be the coarse grain fragments section on the rock identification chart. And so you don't need to memorize porphyritic, but this is something you guys will encounter, is you will see rocks with coarse grain fragments. And another example of that is actually this picture as well. This one would be fine grain fragments, because you could see the dark grains here. They're just fine grains, so they're smaller. So again, coarse is larger crystals, larger grains, and fine is smaller. And so this picture right here to the left on your chart would be fine grain fragments. This picture here would be coarse grain fragments, as opposed to just coarse grain or just fine grain. And then the last section, the last category on that part of the chart is something called vesicular. And what that means is holes. So if you see the word vesicles, think holes. And there's only a couple igneous rocks that have these holes. As you can see, this bottom picture here, you'll see on the chart, first you're gonna, if you do see a rock with holes, just see if it's darker colored or lighter colored, and that'll take you to the rock name. There's only gonna be, I think, 1 or 2 options to choose from. And so these are what the holes look like. So if you see a rock that looks like this, think vesicular, think holes, think vesicles. And these form from gas, from the magma, from the volcanic gas within the magma. And then it pretty much just gets almost not necessarily trapped within there, but it just kind of forms this porous looking rock. And you'll be able to tell these right away almost. They just look like whole, it's almost like a sponge, if you will. It looks like a hardened dark sponge, or maybe lighter colored. But for the most part, if you do see holes within a rock, it'll be relatively easy to identify. And then just the next property will be color. Is a darker light, and then it'll just take you to the rock name. And that's another thing that's going to help, that you guys will use to determine the rock type, is color. And ignore the typo there for determining. Don't know how that happened. So you don't need to memorize mafic or felsic. It's just a term pretty much just that describes the color of igneous rocks. Just think dark colored or light colored. So once, taking a step back here, once you identified if it's coarse grained, fine grained, or coarse fragments or fine fragments, the next part's going to be color. And this is a good example of kind of like a dark color, like this piece of, I think this is gabbro right here, or something lighter colored, or felsic. So this is just to give you a visual of pretty much darker or lighter colored. And this one, again, is pretty straightforward. There will be some in-betweens, like some grays, but just think from, dark, like to dark gray, blackish color, all the way up to lightish, like a whiter, like a light gray to a whiter color, if you will. And the in-between would be just almost gray. And so that's the next step. Once you identify coarse grain versus fine grained, or vesicular, or glassy, is going to be identifying the color. And then from there, it should pretty much be a little bit more straightforward, if that makes sense. And then again, just make sure to be able to distinguish that some rocks will have large grains within smaller grains. So when you, that's just, again, kind of reiterate, this picture right here on the top would be coarse grain fragments. This is just an example of that. So just make sure to look for that. And then again, vesicles, if you see vesicular or vesicles, think holes. If you have holes within the rock, if it looks like a sponge, if you will, then the next step would be color, and then you'll get the rock. And then this is just expanding upon more of the colors. So lighter colors are usually rich in feldspar and silica. Darker colors are usually rich in iron and magnesium. You're not going to necessarily be quizzed on this, but this is just, again, for your reference. And now the only exception is going to be, again, the obsidian. And the obsidian is it's pretty much the black glass. It's the dark looking glass color. So like here, this top left photo is obsidian. If this is not a great photo, but it gets the job done. So it looks like black glass. So that's your only exception. You can say, technically, it's really fine grained, if you will, but you won't be able to see it. It'll be smooth. It'll be very reflective. And again, it'll be just like glass. It's black glass. And so that is a section on the mineral identification chart, but it's the only rock that's under glassy. So you'll be able to identify obsidian once you see it. And now this is not the rock identification chart you will be using. This is another one that's a bit more thorough. Again, if this is too confusing, I understand this. Again, this is just for your reference if you want some more information on kind of how these rocks are classified. The one you guys have is on Canvas. It's linked on Canvas under the question that pertains to it. And it's much more straightforward. But this is just another chart just for your reference. And then lastly, this is the very last part of the lab, is something called Bowen's reaction series. So what this is kind of a chart that gives you a visual on how the type of igneous rock is formed based off its magma temperature, if you will. So on the left here, we have pretty much the temperature at which the magma cools. So if it crystallizes, if you will. So if it crystallizes at a higher temperature, it cools at a higher, if it forms at a higher temperature, I should say. So if you have magma that forms at a higher temperature and crystallizes at a higher temperature, well, the mineral that it might include that does that, if you will, is going to be olivine. And so when you kind of reference this over, the type of igneous rock you have is going to be ultramafic, and the name of that rock would be peridotite. So I hope that makes sense. So you have magma here, and then if magma cools at a higher temperature, it's going to be an ultramafic rock. And if it's gonna have olivine in it, it's gonna be peridotite. And you'll be able to identify peridotite when you see it, because olivine is relatively distinct within igneous rocks. It'll be green, and it's gonna be like a green and black rock, if you will, and you'll be able to identify it. So I hope that makes sense. I'll do, like, another example would be if something crystallizes at a very low temperature. Well, then if the magma cools and it solidifies at a relatively low temperature, then it could include a few more different minerals within it. So you have something that's granitic. So if something crystallizes at a very low temperature, it can include quartz, it can include mica, it can include feldspar. It'll be a granitic, and so it'll be a granitic type of igneous rock. And then granitic And then those rocks could either be rhyolite or granite. But yeah, so that's kind of how you read the Bowen's reaction series. You have the temperature at which the magma begins to solidify, and then you just reference that over to the type of igneous rock that will be. I hope that makes sense. Again, just another example. If you have something if you have magma that cools at a relatively low temperature, but not the lowest temperature, you can have the biotite, you can have mica in there, you can have amphibole in there. You'll have something that's andesitic. And now these rocks do relatively look very close. So that's just to give you a heads up. These like andesite and granite, they do look very alike, very close to each other. Andesite, rhyolite, some samples, they look almost exactly like each other. But yeah, so this is just to give you a visual of how igneous rocks form at different temperatures. And so it's really just, again, just based off the magma. When does the magma start cooling? When does the magma start hardening, if I should say? If it starts solidifying at a higher temperature, you'll get a more ultramafic rock. And so that's how to kind of read the Bowen's reaction series. I believe that's the last slide. Yes. So that's pretty much it for this lab. Again, if you have any more questions, please feel free to reach out. Please let me know. More than happy to help. Again, any question is important. There's no such thing as a stupid question. If you have any questions at all, please let me know. I'm here to help you. And so yeah, I hope this helps. And yeah, have a great week, everyone, and good luck.